Yeah. So welcome back. 16 November, CSE 241. We're in module 5, system architecture part 1. There is a part 2. That's module 6. If you look at the calendar, I just want to call out that we'll be blitzing the rest of material. Quick review of the rest of system architecture part 1 today. We will take up a quick review of module 6 material on Friday and on Monday. So we'll have 2 short solutions and a quick related assignment for you to complete between now and next Wednesday. Next Wednesday is actually a study day instead of a class day. We could opt to host a class during study day, but that would only be for a rare circumstance that we could not finish review of material or needed to do other things. Essentially, what we want to do is set the stage so that students can log a first attempt of the assessment for System Architecture Part 1 and System Architecture Part 2 before we break for the Thanksgiving holiday, okay? So the study day is on the 23rd, and that would be a good opportunity to brush up, review, and log a first attempt. To resubmit anything that needs to be resubmitted, by the end of this week, we'll have all of the credit logged for previous submissions. We've been holding out and waiting for certain individuals, but we can't do that anymore. You will get a chance to reconcile and retake things when we come back. Does everybody know what happens the week after, this week here? It's finals week, yes. So when we post the final exam, it will be made available in accordance with the official exam schedule for UVI that's posted online. But that does not mean you are required to engage the final exam during that time period. It will not be a proctored 2-hour exam in a given location where you come to a room. Instead, you'll have the final exam available if you need to take it per the exam schedule because you have other obligations that week. The intent of the UVI exam schedule is to allow students to effectively manage their final obligations in each of their courses during that last week. So you may have other obligations you need to see about. As an option, you can take take the exam and start it at any point, so long as everything you need to complete for the course is submitted by 11:59 p.m. on 3 December. I say again, you have the option to postpone your engagement of the final exam, so long as everything you need to submit for your final grade in this course is uploaded and done by 11:59, 3 December, Saturday. Are there any questions about our timeline and how we're going to be pushing hard, finishing strong for the finish line at the end of our semester? Any questions? Okay. So this is basically, I hope you've had a chance to just get online and take a look at motherboards. It helps to practice this kind of thing. We said that it's important for you. One of our student learning objectives is that you identify the components given a picture, right? Oh boy, here we go. Yeah, I am not a robot. So there's a fire hydrant. Do any of you get this on occasion?
On a regular basis.
I think one time.
On occasion, yeah. Okay. So So if you just Google computer motherboards and then start taking a look at some of these, is it possible that I could include a diagram like this one and ask you to identify which part of the motherboard you see the most input output? And at that point, you'd be pointing to this part of the motherboard and this part of the motherboard. This special expansion slot, this is typically the high performance expansion slot that's included in most system boards, that's tied to the front side bus or north bridge part of the data bus, right? So where do we find memory in this picture? RAM.
Yellow and red slots next to the CPU.
Yes, thank you. Yellow and red slots next to the CPU. These are called DIMM slots, or dual inline memory module slots. And depending on the age and generation of the motherboard, the production version of the motherboard, in some cases you'd have, DDR2, DDR3, DDR4. There are links that discuss double data rates and what that means. In some cases, you're supposed to put memory in pairs so that they can work in tandem. If you take a 4 gig memory module and you put a 2 gig memory module next to it, because it's a different size, that can actually cause a decline in RAM access and performance. It's best to put, in most motherboards, it's best to put DIMMs in sets. So you'd want to put them in pairs, and in some cases in threes. There were some MacBook Pros, actually some Mac Pros designs, and some other high performance designs that actually had them in threes. So you'll find some server diagrams where you need to put in 3 modules instead of 2, so triplets instead of dual modules. That allows the system to do something called interleaving, where the memory works in tandem, and it's much faster. There's a much higher performance gain. This is probably the chip for, and I'll tell you, BIOS and chipset. Every motherboard has a chipset or a controller that manages the data buses, the north side and the north bridge and south bridge. So quite often you'll see a heat sink and something that looks like a CPU that's mounted on the motherboard directly, but it's not. It's not. In other cases, it may be an integrated graphics card if the motherboard design includes a built-in graphics controller. So that's also possible. What is this right here? Anyone?
It's the internal battery.
It's the internal battery, yes. There's a button cell. You can buy these in Office Max and in Kmart and in Home Depot. Basically, your motherboards all have a battery that help it retain the date and time. It's so that you can retain the settings of the BIOS. If this battery goes bad, the BIOS settings revert to default settings, and every time you power it on, you'll notice that it's some obscure date like 2010 or 2020, depending on how old. If it's a really old motherboard, it'll default to the year 2000. So it's January 1st, year 2000, when you turn on the screen, and then you always having to set the date and time because that's off. That's what this battery does. So that's a very important component. It's recommended that you replace this like every 3 to 5 years. And A lot of people don't know that, but that's one reason why system starts acting up and it doesn't take updates or BIOS flashes. Any questions about this? Again, please take the time to just view random images of motherboards so that you can familiarize yourself with different layouts, because every manufacturer is a little different. And what you want to do is to just have a little practice so that you are not, completely taken aback. This is a motherboard that's typical for a server. In a server configuration, you'd have a lot more slots for RAM. And this is a dual socket motherboard, which allows for more than one CPU. These could be AMD Athlon or Intel Xeon. Let's see if we can we zoom in all the way? Can't really zoom in. Oh, yeah. So this could be like a RISC design for IBM. They had some specialized CPUs for some of their motherboards. So, yeah, there have been a variety of specialized server CPUs over the years. And this is something that you just want to be able to deal with. A lot of your input output is over here. Here's a single expansion slot. So you can add a card. Let's see if there's one other one for quick reference. This is a pretty decent. Oh, yeah, we'll continue because it's. Everybody see this one? Whoop. We don't seem to be able to roll down very much. Can anyone see the BIOS chip on this motherboard? BIOS chip. EEPROM. It's an older looking integrated circuit type chip, and it's typically found near the battery. It's right.
So with a white lettering?
Yeah, it's right here. This is the BIOS chip. So in an older motherboard where you don't have UEFI for your BIOS post instructions, you have a traditional EEPROM or double EEPROM chip, and this is a classic presentation. This is an older motherboard, much older motherboard. Because of the power connections, this is an older style of power connections. These are older style hard disk connections. So we used to connect hard drives with a parallel ribbon cable. And this is likely an IDE or possibly a SCSI. I'd have to zoom in and look closer. This is a dead giveaway. A lot of CPUs run hot, so a cooling fan on top of the socket is a dead giveaway that that's where you have. This region itself is the front side bus, right? The input output to older style hard drives and for expansion slots, and the input output on this side, this would all be south side or south bridge. Excuse me, not north side. North bridge versus south bridge for your data bus, right? That's what we're talking about. Any questions? One of the things we wanted to impress upon you is that there is a hierarchy or scale of memory performance and expense and capacity. And this table lists memory from the fastest the extreme most performance to the slowest performance. So you have USB and other external hard drives that are connecting through a USB port. The further away you get from the CPU, the slower the performance, but the greater the capacity. So the size of the memory increases as you move down the chart. Its performance decreases as you move down the chart, and its cost decreases further down the chart. So once again, as you move down the chart, the size and capacity of the memory increases, the performance decreases, and the cost decreases. So this would be the very fastest memory apart from registers on the CPU itself, the level 1 cache made out of static RAM. This is where you get to RAM. This is RAM right here, what we would call traditional RAM. And yes, it's in gigabytes right now. So I remember a time when having a single megabyte of RAM was a very cool thing. But that was another lifetime about 35 years ago. And I actually bought one of the original IBM PC-ATs, Advanced Technologies, and it sported a 16-bit processor, an 8286, and it actually had a Hercules graphics card that could display better resolution on the green screen. There was only one color, green screen, and yes, it booted with floppy disks. But I also had a 20 megabyte hard disk. I'm not making this up. This chart is another representation of the progression of memory types, where it shows CPU registers first on the chip, L1, L2, and then L3 is off the chip, but still on the die. So L3 is still on the die, or it's on the package rather. These are in the die. All right, so let's refine that understanding. If the die is the actual chip, L1 and L2 are in the die. This is next to the die in the package, so it's still in the socket. It's on the physical package of the chip. Everybody understands what I mean by package, right? Package. We went over that, didn't we? Thought we did. Yes, no, maybe, package.
Mm,
Yeah, it's in there. Here's the main memory RAM, and here's secondary storage, virtual memory. Virtual memory is a way of extending your RAM. It uses fast, contiguous disk space. In theory, your hard disk has sections, well, traditional hard disks have sectors of the physical media that are quicker to access than other sectors further out on the disk. So there are spinning platters. It's like a, we'll get to that in a minute. I'm going to come back to this secondary storage for virtual memory. Every time you see a link, you need to click it. Did I mention? Every time you see a link, you need to click it. Right?
yeah.
Okay.
Yeah, you mentioned that.
Yeah. Now you have many generations of the iCore product line, so there have been some enhancements. The latest ones are significantly different, right? So years ago, when the Intel i7 processor came out, it was latest, greatest, and since then, the 12th generation of Intel processor includes performance cores and efficiency cores. So this is something that's another trend. So this is something that's a relatively recent development. So when we talk about how CPUs are designed now, this is a huge change from what you're seeing. I'll probably add this information to an update for the addendum. We'll work an addendum that supplements the study guide, but what you see here is on the die of the 12th generation, I think beginning with the 10th or 11th generation, they started doing this. They have what they call performance cores, and these are hyper-threaded. The efficiency cores are not hyper-threaded typically. So E-core delivers single-threaded and multi-threaded workloads. So the performance cores, if they're hyper-threaded for the operating system, what that means is that you basically have 2 virtual CPUs for every physical CPU. In this case, you'd have 8 physical cores, each hyper-threaded. So you have the equivalent of 16 virtual CPUs. Each of the efficiency cores is the equivalent of a single virtual CPU. So what's going on here? Well, for burst mode and for really vigorous multitasking, for heavy loads on a system, gaming, high performance workstations, supercomputing, and so on, when you're maxing out your CPU load, the performance cores come in a big way, but the E-cores take care of basic things. The typical overhead that every system has, you know, boot activities, basic memory access, and so on. So E-cores are designed to provide more efficient background and under the hood operations, the overhead of running an operating system. So this is something they did to basically make things more efficient. Now, if you wanted to know what and that's on a single processor die, right? So on a single processor die, this is what you have. The thing to remember is that each of the E-cores only have a single virtual CPU, where these have a double. So the total number of virtual CPUs this system could support would be the number of P-cores times 2 and the number of E-cores times 1. So I have 8 E-cores. Those are 8 virtual cores. I have 8 performance cores. That's actually 16. What's 16 plus 8? 16.
24.
Yeah, it's 16 plus 8 is 24, right? So the total number of virtual CPUs this chip, this single die carries is 24 virtual cores. That's pretty good. That's pretty decent. It's not uncommon for Threadrippers, AMD Threadrippers, to have 12, 16, or 24 cores, each of which are hyper-threaded. So an AMD Threadripper might cost $1,000 to $2,000 depending on the generation and the model, but you can have up to 48 virtual processors on a AMD workstation with 24 physical cores, hyper-threaded, 48 total virtual CPUs. That is one smoking machine. And then if you add a graphics controller like a 3080 or something like that, you're really, really smoking.
These are expensive.
Oh yeah, they're very expensive. Yeah, you're putting a couple of grand into each one of those components by the time you finish. So, you know, we've already talked about not confusing your terms. The package that conveniently combines the ALU registers, L1 and L2 caches, right? That's in the package that goes in the socket. This is the important thing that I want you to understand about this. So what's going on here? and we need to call this out in a big way. Efficiency experts. So about 100 years ago, when the Industrial Revolution came about, some companies discovered the idea of division of labor. And so they would have assembly lines in factories where the workers in the factories would do one thing, but learn that one thing and perform it very, very well. And along that same era, the profession of efficiency engineering was birthed, right? So you have professional efficiency engineers, and their job is to figure out how to squeeze more performance out of limited resources. That said, for quite some time, there's a relationship that's been discovered, and it's kind of a time-honored thing. It's called the 80-20 rule. Now, the 80-20 rule basically means, in a nutshell, and this is a very common language description of what the 80-20 rule is. Let's pretend that the computer you're looking at is actually a toolbox in your house. We're gonna equate or compare your household tools with the memory resources of a computer chip, a computer system, an entire system architecture. Is everybody with me? Resources.
Yes.
Resources in the system architecture are like a big toolbox in your home. And what efficiency experts have come to understand is that 80% of the time you are using 20% of the tools. Let's repeat that. 80% of the time in any given household, you are using only 20% of the tools. Now, you have other tools in the toolbox. You have other resources on a system, but 80% of the time, and you have other data on a system. The 80-20 rule repeats over and over and over again. When you look at how somebody organizes their office space, a lot of people instinctively keep the things they use more often closer to them. 80-20 rule. 80% of the time you're using 20% of the stuff you have. This is just a natural phenomenon, the 80-20 rule. Now, there are other names for the 80-20 rule. Sometimes it's called the ZIPS, spelled ZIPF, or Pareto's, Pareto paradigm. There's all sorts of different names for this thing, but essentially, I call it the 80-20 rule. Now, the data that a CPU is working with, a lot of times the data that a CPU is computing and executing, well, 80% of the time, it's 20% of the data they need, which means that if you have faster memory in closer, you can make things much more efficient by magnitudes of scale. What are we saying? A magnitude of scale is like 10 or 100 or 1,000 times. It's a significant factor of increase. So when you say a scale of magnitude, we're saying it's a multiple, and it's not just a little multiple. It's a huge increase, right? So if you do certain things, and this is just human habit, if you use your system or device for certain activities, well, most of the day, you're using 20% of the stuff 80% of the time. If you pre-position that information, the faster, more expensive memory closer to the CPU, then it's utilized much quicker when it's called for. The closer you can get to the CPU, the faster it can be utilized, and you can turn around much quicker. The problem is that the further distance you get from the CPU, there's more overhead, so it takes longer to do this. So 80% of the time you're using 20% of the data. On this level, 80% of the time you're using 20% of the data. On this level, 80% of the time you're using 20% of the data. On this level, this is what comes into play with something called caching or buffers. When you have hardware components that are extra layers of fast memory, you have hard disks that have very fast RAM or very fast non-volatile, in some cases non-volatile. So you have buffers that of different types. Some are volatile, some are non-volatile. What are we saying? Depending on the device and what kind of data you're moving on it, there's memory, it's electronic memory, and it's added to the disk. So we have spinning hard disks that are slow as molasses in January. The spinning hard disks are down here. But even those hard disks have something called a buffer. So it's fast electronic non-volatile memory that's stitched onto the front of the case of the hard disk. And it's storing what? Oh, the 20% of what it uses 80% of the time. Does everybody understand what I'm talking about here? The 80-20 rule.
Yeah, mhm.
Yeah, it's not, it is, so in terms of design, it's one of those classical things that keeps coming up over and over again. Spatial and temporal locality. When we say spatial, we're talking about distance. When we say temporal, we're talking about number of system clock cycles, time intervals, right? Number of milliseconds or nanoseconds. This we're talking about distance. This we're talking about time. The idea of locality. Put the things that you use more recently or more commonly or more often closer in terms of distance and available within fewer clock cycles. That's the goal of buffers and caches. Now, when we're loading memory, there's something that needs to be understood. There are different models, first in, first out. FIFO means first in, first out, right? So when data is accessed, depending on the type of memory, a different model of access is in play. Static RAM cache uses first in, first out. Well, that makes sense because it's closer. If it's first in, it's first out, it's probably what you're going to use the most. That's what static RAM does. The other types of memory work differently. It's first in, last out. So when we're talking about the differences between these two access, this is a virtual layer with the hard disk, right? It's first in, last out. That's the algorithm or method where memory is accessed for hard disks that are providing what's called page or swap file memory. This layer of hard disk memory supplements the RAM. You take what's stored in RAM, and if you're multitasking and it's just sitting there, your system will swap it out. It's also called swap memory, page file memory, virtual memory. It's not real RAM, but it's a huge chunk of RAM data that's written to the disk temporarily in the fastest part of the disk. Okay? So that's what we're dealing with. What we have here is a different model of memory and data access because of the differences in physical mechanism, the locality, the distance and time criteria for each of those different memory types. So when you're dealing with hard disk and virtual memory, it's first in, last out. When you're dealing with cache or buffer memory, super fast memory, very expensive memory that's closest to the CPU, the loop is much tighter. So it's first in, first out. Are there any questions about these two different load algorithms? Memory loading algorithms, right?
So since um SRAM is like the one that deals with accessing data quicker,
Correct.
that would deal with Philo. And so that means DRAM would be wait, wait,
SRAM would be FIFO.
that's all. And then SDRAM would be Philo then.
Well, SDRAM is standard RAM. So when you think of SRAM, it's not It's not dynamic RAM, it's static RAM. So the S for SDRAM, it's not the same as SRAM. The S for SRAM is static RAM.
Mhm.
When you're talking about common system RAM, like the DIMM modules, that's synchronous dynamic random access memory. So one of the innovations of RAM that's so important, I'm glad you asked that question, by the way, because it's kind of a great segue to call out the differences. Static RAM is really super fast stuff closer to the CPU, and those are level 1, level 2, level 3 caches. When you get to system memory, synchronous, right? Synchronous dynamic random access memory, not static dynamic. Those two terms are different, right? Static means fixed or unchanging. Dynamic means, okay, constantly changing, right? When you have system RAM, it's fluid. It changes constantly. That's why the term dynamic is in the mix. That's when you're multitasking, when you're switching screens, when you're juggling applications. The random access memory is the content of that is changing in a different manner, and it's tied to the virtual memory. So it follows the Philo model, especially where virtual memory or swap memory is concerned, okay? So it has to, and the other thing too is, if we're using analogies, I want you to think of the RAM as being the active workspace. So if we use the analogy of a workshop, if you had a workshop, a tool shop or a workshop for a hobby, and you go inside that workshop, you would have a table or a workbench. That's the equivalent of RAM, okay? And the shelves and bins, the storage to the side, and on the floor and along the walls, you have storage bins. That's the equivalent of a hard disk, right? Now, if you have a very, very small table, you have to go back and forth to the storage bins and the shelves on the wall a lot more often. Put another way, if you have plenty of RAM, SDRAM, your hard disk is going to last a lot longer. If you have less SDRAM, your hard disk is going to wear out very quick, okay? Now, what I'd like you to do is to go ahead and if you scan the rest of this study guide, you're going to find that it talks about the different kinds of RAM. There's a specialty RAM, like for video cards or graphics RAM. It's dual ported, which means you can input and output at the same time simultaneously. So it's RAM, but it's modified RAM. We've already talked about interleaving or working in tandem or with banks, dual DIMMs or triple DIMMs, right? And we've touched on page or virtual memory. So here's more information, right? This is the view of a traditional hard drive. You have a spinning metal platter that's coated with magnetic stuff, and this arm on the end has a read-write head right here. And it is 1/1000th of an inch away from the surface. When you take a traditional hard drive and you drop it, that read head tends to impact on the metal surface and you get memory corruption. That's why traditional hard disks aren't good in a laptop. I realize that we are coming up on the end of the session. SSD RAM is an innovation that's pretty serious, but there's other considerations for how SD-RAM works. And what I'd like you to do is go ahead and, oh yeah, this one. So this is an original hard disk from 35 years ago. I actually worked on these when I was in the US Army working with nuclear weapons 35 years ago in Augsburg, Germany in 1986. So I'm really dating myself here. It was a 10 megabyte drive. The platters were huge. So the discs were huge. This thing was the size of a toaster. It weighed 20 pounds. It cost $2,500. And it sounded like a jet engine when you powered it on. It would just have this really whiny, you could hear this thing like cranking up. And it was so cool because you didn't have to swap a bunch of floppy disks in and out of a disk drive manually, right? Please go ahead and scan ahead to the end of this study guide. It's an easy read. There's lots of big pictures. We'll wrap up in the first part of our session on Friday before we start Module 6 material. If you need to peel off to get to another class, please do so. We will see you on Friday. Thanks for joining us. Any
Yeah,
questions?
okay.
Yeah. Bye-bye for now.